Good afternoon, everybody. Welcome to Zoom for Wednesday, Chem241. We'll be finishing up Chapter 4 at the beginning, and then moving on to Chapter 5. This is called a titration curve. Let's take a look at it. What's happening is we're starting with a mixture, not a mixture. We're starting with an acid, HA, and when we're done, we have no more HA. What happened was HA is reacting with a base, and it's becoming A minus. And we're getting the conjugate acid of the original base. So that's what's happening. And the reaction, the mathematical reaction, equation that governs this curve is called the Henderson Hasselbalch equation, where the base is on top and the acid's on the bottom. And the question for you is, why does the pH change so little in this area here? And the answer to that question is we have a buffer in this area. Buffers are good between pH equals pKa plus or minus 2. What does that mean? Well, if you have an acid with a pKa of 5, like a carboxylic acid, you can use a mixture of the carboxylic acid and its conjugate base to make buffers anywhere from pH 3, which is 2 below the pKa of 5, up to 7, which is 2 above the pKa of 5. Another example would be a mixture of an ammonium ion and its conjugate base, an amine. An ammonium ion has a pKa of 10. You could make a buffer of that mixture anywhere from pH equals 8, which is 2 below 10, all the way up to 12, which is 2 above 10. Outside of those ranges, one of the components of the buffer is gone. And if you look at this being a log scale, you can have 100 times more A minus than HA, and then the log of 100 would be 2. That would be the top end of the buffer scale. And flip it, you could have a ratio of 1 to 100 of A minus over HA. Then you have the log of 1 over 100, which is negative 2. So if you have more than 100 to 1 ratio of either species over the other, you have not enough of the 1 and too much of the 100 or more. So that's your allowed buffer range. So what's going on here is we're adding a base to our buffer. Initially, till you get to the zone, the pH goes up, and then you're in the zone. It resists change because the base is reacting instead of with water, it's reacting with HA. Conversely, if you're over here and you started adding an acid, you'd have another titration curve coming the other direction. Yeah, this is a reversible situation. The most interesting point on the curve is the point at which you have 50% of each chemical. How do you know when you have that? Well, you do the titration, you get your curve, and you'll see at the very end, this thing is just skyrocketing in pH because every bit of hydroxide you add now, when the HA is gone, just becomes hydroxide in solution. And that makes the hydronium ion go down directly. Remember, the product of hydroxide times hydronium is a constant. So the pH is skyrocketing. So you take the point where the pH skyrockets, that was the end of the titration. You divide by 2, and that's halfway through the titration. And that's the time where HA is equal to A minus. The concentrations are equal. Do the math. If you put a number here, pick a number, any number, say 4. 4 over 4 is 1. Log of 1 is 0. pH equals pKa. So right here, the pH equals pKa because you're at the halfway point. So that's the nice use of this titration curve. Now, why are buffers important? They're incredibly important. We owe our lives to them. Let's just take it in a very general sense. Reactions in biological systems are catalyzed by enzymes. Okay? Enzymes are in a broader category of molecules called proteins. Proteins, the only important thing about proteins, or the most important thing about proteins, is their shape. Their shape is very sensitive to things like intramolecular hydrogen bonding. Hydrogen bonding within the structure of a protein where there's amides that have H bonded to N, and there's alcohols in some of the functional groups of a protein. There's a lot of things that can hydrogen bond with each other. When you change pH, you're changing the number of hydronium ions available in solution. Now, if you are an oxygen, what are you more interested in hydrogen bonding with? A hydronium ion hydrogen or a H attached to an amide? I'll tell you what you're more interested in bonding or hydrogen bonding to. It's a hydronium ion. It's a much more positive H. So by changing the concentration of hydronium ion, you're taking the enzyme's shape and changing it by interrupting the normal hydrogen bonding. And when you change the shape of a protein, its ability to catalyze reactions is drastically lowered. Enzymes have evolved over time to have optimal pHs, generally 7.4, which is called physiological pH, at which they operate their most efficiently. If that pH is changed even a little, even by 0.1, then that enzyme will be slowing down and you'll have metabolism issues. So your blood is well buffered at 7.4, which is called physiological pH. Please learn that. Anything below 7.35, your protein shapes change so much you start getting ill. It's called acidosis. Anything above 7.44, your protein shape changes so much you start suffering consequences. It's called alkalosis. So to maintain protein shape in their ideal form, we need blood buffered at 7.4, and we need that buffer to be rock solid. And that buffer contains bicarbonate and carbonic acid. And you can use the pKa of carbonic acid to figure out the ratio of the two species is roughly 11:1 in solution, but I'm not going to make you do that on a test. You can read about it in the book. We are going to finish with a sample problem similar to the buffer problem we ended last lecture with, but going in the opposite direction. So you have at least one example of each type of reaction, and I've copied the problem over on the next page, so you have a blank for, no, I didn't. I thought I did. That is page 2 right here. Page 1. Page 1 just has the problem. Not the order that I intended, but we can work with it. So I've named our molecule after Justice Ginsburg. I called it Ginsburgium in a short form RBG. And I've given you 4 pKa's. So here's what's going to happen on the problem set and on the exam. You're going to look at this problem and you're going to see he gave us 4 pKa's. Or maybe I'll give you 5. Maybe I'll give you 3. The number of pKa's I give you tells you how many H's are in the fully protonated version of the molecule. So if I give you 4 pKa's, come up with a short form for the fully protonated. Might as well go with our short form in the question here. You can call it H4A if you want, even in this problem. I'll call it H4RBG. And it's got a pKa of 2.3. You know how I know that? The one with the most protons is always the most acidic. The next species, and you should know which species is which here, would be it would have, you took away a proton from something that was neutral, it's going to be an anion now. Not critical to solving this problem, but please acknowledge that you know every time you take away a proton, the charge becomes negative by 1. This is the second one. And the third one would be H2 RBG -2. And that would be this third number here. And our last one would be having only one proton, HRBG -3. And let's look at the words in the question and figure out which species we're actually starting this problem with. And the answer to that is right here. Sorry, I've been writing all over it, but this is a very important word right here. Which of the 4 species over here is the one that is monoprotonated? It's this one. Now on your problem set, I'm going to have a big list of, you know how it works. There's going to be a big table. Some of you are going to have a monoprotonated version of the same molecule. Some will be diprotonated. That'll be this one. Some of you will be triprotonated. That'll be this one. And some of you will be fully protonated. Okay, if I gave you 4 pKa's, the fully protonated is right there. It's very important to know where you're starting in this problem. So we're not starting with anything except for this species here that has 1 proton, HRBG -3. What's it reacting with? How much is there of it first? That's 3 moles. And it's reacting with a strong acid. In this question, unlike the one last day on Monday, we're adding a strong acid. This question will not be done until our strong acid has been completely reacted. So 6.9 moles, we got a long ways to go because we can only go 3 moles at a time with each species that we create. What are we creating? You're giving a proton to HRBG -3. It's becoming H2. It's becoming the diprotonated species. And Cl-, I'm just going to write my usual comment, who cares? It is a spectator anion. It doesn't have any influence on the pH. And we always do these problems where we have an initial and a change and an end. Truth be told, I don't even need to see those letters. Which one's the limiting reactant here? Well, it's the 3. It will react completely. It will take 3 moles of HCl with it. It will create 3 moles of HRBG -2 and Cl-, I already said I don't care. So you're left with 3.9 moles of HCl. You're not done. You know you're not done. You don't have 0 moles of HCl. You got a new ice problem coming up where you start with H2RBG -2. Oh, let's try to save a little writing. Oh, that's nice. And one more time, just for good measure. You know how I know I need at least 2 more ice problems is because this number is still greater than 3. This time you have no more HRBG -3. You have H2RBG -2. You still have HCl. You're going to create a different species this time. You're going to create H3RBG-. And forget about Cl-. We started with 3 moles of this thing at the end of ice 1. We still had 3.9 moles of this. We don't have any of this yet until we react all 3 of this, the limiting. Going to lose 3 HCl's. We're going to gain 3 of these. 0 of that, so it's no longer in play. 0.9 HCl means we're not done yet. And you've made 3 moles of this. Final ice problem. H3, oh, pen's off. And now it's black. H3RBG negative. It's going to react with HCl. So finally we know what the acid in our buffer is. It is the one with the fully protonated RBG. And we started with 3 of this one. Started with 0.9. Ah, which one's limiting now? HCl. You know this is the last ice because you're down to 0 moles of strong acid. You're reacting 0.9 of this, you're left with 2.1. You're creating 0.9 of this. Here is your mixture at the very end of this problem. The question is, which piece is the acid in this buffer? And it's the one with the extra proton. Then you go back to your preliminary work. This is the acid. It's got the extra proton. What was the pKa of that acid? That preliminary work was not wasted time. That was 2.3. Your answer has to be very close to 2.3. That's what buffers do. They keep pH close to pKa. The only remaining question is it a little above 2.3? Is it exactly 2.3? Or is it a little below 2.3? And the answer is a little above. And did I just invent that out of the blue? Now, if it was a multiple choice, which it won't be, some of you know that already, say 2.4. You don't have a calculator, don't need a calculator. Give me an answer that's just a hair above 2.3 and you got the right answer. The reason why I chose a little above 2.3 is we have more base than acid. 2.1 is a bigger number of moles than 0.9. Acids raise pH. In a buffer, pH is always close to pKa. That is the end of the story for chapter 4. Buffers are really important. We know why. And I will see you in a few minutes.